So every day the Earth is losing plasma into space. We're talking about 50 to 100,000 tons a year. It's not only plasma, it's also neutrons. And cold plasma, which has been sort of elusive for a long time, actually plays an important role in this course. This is a subject that I will say a few words about in this talk. So this is a collaborative effort. I've benefited from a number of discussions with experimentalists, modelers, and it has resulted in this presentation. So the outline of the tutorial is as follows. First, a bit about the motivation. Why do we care about ion outflow? And also the definition of cold and polar cap. Then we go and do a bit of basic physics and ask ourselves why would ions or matter escape at all. Then we go to some recent observations from mainly from the cluster spacecraft, where we look into how much core plasma escapes, what the role of solar activity and geoactivity is, and of course, what happens to this plasma, the fate of this plasma. And if time permits, perhaps a few words about the global context. So, Ray Chappell already mentioned some of the motivation for studying cold plasma. It is an important source of plasma for our magnetosphere, in addition to the solar wind. So solar wind can come either day-side reconnection, direct entry via the cusp. We can have high latitude reconnection, and of course along the flanks. But still, the ionosphere is an important supplier of plasma to the magnetosphere. So even if you don't care about ion outflow as a process, if you work in the magnetosphere, with the ring current or radiation belts, recall that much of the plasma that you're working with actually comes from the ionosphere. So when we discuss outflow, we often divide into three different sources. There's the cusp, characterized by precipitation, we have waves, we have pointing flux, and all kinds of processes. On the other side, we have the auroral zone, which is perhaps even more dramatic. We have precipitation again, we have field-line currents, so we set up parallel electric fields, we get Joule heating, and so on and so on. And both these two things have been quite extensively studied. In the middle, we have the open polar cap. So part of the polar cap is you have open field lines, so there is no hydrostatic equilibrium. So in a sense, the electrons, very low energy electrons, they can sort of escape simply by thermal effects. You set up an electric field, and you can eventually drag out the ions, low energy ions, also from this region. This has been partly from the early models, concepts, Banks and Holster, Axford, polar wind concept should be known for most of it. Later also found in experimental data. More about the motivation, Rick already mentioned it. The ionosphere is a very important source, but until recently, it was sort of invisible. So in the Chappell paper from 1987, it actually says there is an invisible component of cold plasma, less than 10 eV, that has not been observed. Now, almost 3 decades later, we can say that this invisible component is actually visible. So Mats André had turned it previously given. Okay, let's go to some basic physics here. Why do matter escape? Well, we can set up a simple force balance equation here. So there's a force working down, essentially the gravity tries to keep the plasma on ground or in the atmosphere. On the other hand, there will be forces that work upwards. So for neutrals, this is typically thermal forces, pressure from below. If you go to ions, which is the focus of our group, we have additional electromagnetic forces. We can also cast this force problem into an energy balance setup. So you balance the kinetic equation of the material to the potential, gravitational potential energies of the Earth. Then we find that the escape energies here, they are in fact quite low. So we talk about energies of 0.7 eV for protons, and perhaps 10 eV for oxygen. So very low energies. And this is very tricky to measure these kind of energies in classical instruments. The forces we talk about are partly thermal. So the white ones here to the right, we have gravity, of course, which pulls things down. We have thermal forces. And we have a bunch of electromagnetic forces, here printed in yellow in this slide. We have electric fields. We have mirror forces. We can have centrifugal forces, and perhaps other forces that I haven't included. These forces, they don't operate at the same level everywhere. Some of them are only relevant at low altitudes, and some only at higher altitudes. So, for the polar wind, in particular relevant is the ambient electric field. These low energy electrons disappear up for thermal reasons. They set up an electric field, which then can extract the ions. The total potential brought by this ambient electric field is somewhat still discussed. I talked to a couple of people during the poster session yesterday, and they gave me different answers. So the modeler says it's about 5 volts. Experiments indicate it's more up to maybe 20 volts. So there's still some converging to be done here. Okay, one issue that we have when we want to measure these in space is the fact that you have spacecraft charging. If you put the spacecraft into the polar cap, low regions of the Earth, or for that case anywhere, it will be exposed to sunlight. Sunlight means photons, means energy. And this energy can kick out the surface electron, photon emissions from the surface of the spacecraft. So you have a current of electrons going away from the spacecraft. Unless you can balance this current, you will eventually charge your spacecraft. Spacecraft will attain a positive potential. And this is something we can actually measure, because we can have sort of large-scale probes far away from the spacecraft, sitting in the neutral surrounding plasma. And we can measure the voltage difference. And this is an example from the cluster mission, where the spacecraft encounters the low-density lobe for a short interval here. And the spacecraft charges up to 60 volts. It's quite a substantial value. So in these cold ions, recall we talked about escape velocities of 0.7 and 10 eV for protons and oxygen, respectively. When they come up along the field lines. There's not a lot of acceleration, not a lot of heating. When they come up, they see the spacecraft here, sitting at a potential. They will be diverted around. They will never reach the spacecraft. So, however good your particle detector on board this spacecraft is, it doesn't help. Because the particles, they will never come to it. So it means you don't have the full distribution of these particles. You can only measure a part of it. A large part of the lower, the cold ions, they remain invisible due to this. And behind or in the wake downstream of the spacecraft, we also form a wake, which is completely void of ions. The electrons, however, they are much more mobile, so they can fill this wake. And as a result, you set up an electric field, sort of artificial, because it's set up by the spacecraft interaction with the ambient plasma. And this wake electric field is something that we will utilize later. Before we do that, let's see how we could, in theory, measure cold ions. Because there are other methods. We can do it from ground. So this is a picture from Svalbard, the Svalbard ice cap radar, located in the polar cap. And there are studies of ion outflow, actually more upflow, done with with this radar, and perhaps also other ground-based radars. And just one example from a study we did last year. So the left panel here shows from top to bottom temperatures of electrons and ions and velocities. So the last plot and the first panel and the last panel is interesting here. So the last panel shows the upward velocity that we measure with the radar. And the top panel shows the electron temperature. And there is a connection here. Whenever you have heating, additional heating, electron heating, you have upflow. Problems with radars is they only go up to about 1,000, 1,500 kilometers. You can't probe anything above that. So what you see is really upflow. You see something going up, but you don't know how much is coming down or whether it actually escapes and can supply the magnetic field. Another thing you can do, you can use low-orbit spacecraft. Prominent examples are the Tutorial missions and fast missions. But the spacecraft charging issue is less of a problem. They don't attain these very high potentials. Once again, you're not really sure whether all of the plasma that you observe really escape. So it's more like flow. You don't know whether they supply the magnetic field. An even better method is if you can avoid the spacecraft charging totally and try to keep the spacecraft potential to zero. And there are some good examples. So this is, for example, from the Polar spacecraft back in '98. It's a study by Zhu et al., where they actually managed to keep spacecraft potential to zero or a few volts. And they were actually able to use the plasma instruments and derive moments here. So here we see the four panels that you see here. They show the velocity, they show the density, they also show the temperatures. So just for reference, they obtain velocities typically 30 to 40 kilometers per second along the field line. The average or mean is 0.4. They obtain typical densities of 0.3 per cubic centimeter and temperatures around 1 electron volt for a parallel and perpendicular path. This would have been ideal if we could do this all the time. But this is very tricky because you have to neutralize the spacecraft. You need some active experiments. You need to emit ions. And ions is sort of a limited resource. So here, back in 1998, they managed to do it for, I think, 3 orbits. And then the ion emitter was exhausted, or they couldn't do that. Then there is a completely different approach. You don't even try to fight nature. You utilize this wake. You turn this charge into your benefit. And you take the spacecraft potential and you derive the density from that. And you use this artificial wake to determine how fast the bulk motion of these ions. And this is something that the Uppsala team pioneered using cluster data. We'll come back to this. There are a few drawbacks, actually a few perhaps serious drawbacks if you are interested in the composition or if you're interested in moments. This method cannot resolve composition. It's mainly sensitive to protons. And of course, we get no moments here. We can't derive temperatures or we need the distribution functions here. So, the second half of my talk here will be focused around some recent cluster observation. I'll show how they actually do cold ion outflow studies using cluster. For those not familiar with cluster is a full spacecraft ESA NASA mission launched not in 2002 but in 2000. It has a roughly 4 by 19 RE polar orbit, so it goes through the lobes across the polar cap, so it is very well suited for doing outflow studies at high altitudes. The key feature of the cluster spacecraft is that we have 2 complementary electric field instruments. We have a classic double probe instrument called EFW, which is sensitive to this wake. We can actually measure the wake. And we have an electron drift instrument, which actually emits an electron beam many kilometers away, so outside the wake, comes back, and we keep track of this, and then determine the drift of the gyrocenter, which is a function of the electric field. So it's a very precise measurement of the electric field. You can only measure the convective electric field. So we now combine these 2 instruments. Basically, what we do, we derive the density from the spacecraft charging. We use the wake to derive the parallel bulk outflow of these cold ions. We calculate the flux, so we have the flux of cold ion outflow. And if we want, we can go and find an estimate of the polar cap area, and we can calculate the total area. First step, establish the density. We then use a relation between electron density and the spacecraft potential. It's a fairly established method. So there has been a lot of calibration effort for the cluster mission, and I think we have this fairly good in control now. So the densities are fairly accurate, thanks to efforts by a number of people here. Second thing is, this is slightly complicated, but now we want the parallel part of the outflow. And this is what we derive from this wake. So the wake electric field is actually, the velocity of the ions is actually a function of the wake electric field. The larger the wake, the larger the flow. And with some manipulation, we can actually derive the parallel velocity out of this. And this is what we do with cluster. If we want to look at the total outflow rate, we also need an idea about the polar cap size. So what I've done here, and what many people do, they just take the auroral oval and then they move a couple of degrees forward of that, and they say this is the open polar cap. And it actually gives a very good idea about the size of the polar cap. The size of the polar cap can actually vary significantly. So to the left here we have a contracted polar cap, small, which means that our source gradient to cold ion outflow is very small. With disturbed conditions, you get a much more expanded polar cap also. So there's some efforts here, for example, by Milan et al. 2012, where they actually try to parameterize this using the ST index, the storm time index, and the day-side reconnection field. And these are sort of things we have fairly good control over. They found a very good correlation between the polar cap size and these two proxies for opening and closing of flux. So we have the polar cap data. Let me show some results. So these results are based on a number of papers. First of all, there's the original Ewald paper, where he actually derived this method and presented the first data. There's a follow-up paper, fairly recent, by Mats André. Then there are some fascinating studies by Kun Li, where he tried to find out where do these ions really come from. Can we determine whether there are certain regions in the polar cap where we have more or less outflow? And then we will also look at the fate of these ions. Where do they eventually land and under which conditions? So if you take these measurements over many, many years and try to derive distributions, we get typically densities measured by cluster in the lobes up there, so of the order of 0.1 per CCM. There's a tailored distribution here, so the mean is somewhat higher, 0.18 per CCM. Velocities of these cold ions, the peak aligned velocity is 20 to 40 kilometers per second, so slightly lower perhaps than the Sun et al. Results from Bullard. Once again, mean 25 kilometers per second. And if you now calculate flux from these two values, you end up with an outflow of cold ions of the order of 10 to the 8 per square centimeter per second. And if you integrate over the two polar caps to get the total outflow, you end up with like 10 to the 26, 10 to the 25, 10 to the 26 ions per second. And this is actually a quite large number. This is comparable to the studies from other sources, from the crust and from the auroral zone. So cold ions are actually a significant contributor. Ion outflow is, in particular cold ion outflow, is very much modulated by the solar irradiance. Essentially, ionization controls the outflow. So here is a little plot of F10.7 index versus flux. So F10.7 along the horizontal axis, flux along the vertical axis. And there's sort of a almost linear relation in this, well, it's a linear plot. The higher irradiance you have, the more outflow. So it seems that ionization is sort of a prominent driver here, rather than transport out. Just for comparison, if we look at some other sources of plasma to the magnetosphere, I looked up a few papers here and I found that the solar wind can contribute like 10 to the 24 to 10 to the 27 ions per second, mainly protons, bit of helium. High latitude up to 10 to the 27th. There's a fairly recent study here by Shi et al. A couple of years ago, gives these numbers. And the terrestrial outflow of the order of 10 to the 26th, where perhaps under certain conditions the cold outflow actually dominates. So the cold ion outflow is actually a significant contributor to the plasma sheet and to the magnetosphere. Let's go and see a bit more details about the source region here. Where do these particles or where do these cold ions come from? There's an interesting study done by Kun Lee a couple of years ago. He took each of the measurements from the cluster mission and tried to trace them back, follow the particles back to the ionosphere, taking into account whatever forces he could only address gravity and centrifugal acceleration. He had no information about parallel electric field or the mirror force. And he did this for hundreds of thousands of observations, and he was able to create maps of the outflow. So these are maps for northern and southern hemisphere, northern hemisphere and top, southern hemisphere bottom, during 3 different geomagnetic conditions: quiet, moderate, disturbed. So we see 2 things. We see the expansion and contraction of the polar cap, and we see that the outflow is in general higher when you have disturbed conditions. And if you look more carefully, you will see that there are certain regions where we seem to have some additional cold outflow. Mainly the auroral zone, if you see on the right plot here, there's some additional cold outflow also from the sort of auroral region. And if you see the lower plot, there seems to be some additional cold outflow from the region near the cusp. These are regions we normally associate with more energetic, more and more oxygen outflow also. Once again we see the expansion of the polar cap and the enhanced flux during disturbed conditions. Fate of these ions. This is sort of interesting because you always have illumination of the polar cap region in some regions. So there will always be ionization. So during quiet conditions, you still have outflow, you still have this ambient electric field which extracts them, but you have essentially no convection. So whatever comes up of the ionosphere simply flows along the stretched magnetic field lines in the lobes and into the solar wind. So the largest losses into the solar wind are actually during quiet conditions. You go to the opposite case. If you have very disturbed condition, that is the lower panel here, then you have a strong outflow, but you also have a strong convection. So most of the things that come out, they are immediately fed to the magnetosphere and fairly close to the Earth, sort of the inner magnetosphere within perhaps 30, 40 RE. For then intermediate conditions, you get a sort of intermediate outflow, but they are now transported further down tail and potentially have more time to be energized with various processes in the magnetic tail. So, since we still have a few minutes, a few words about the global balance here. So, 10 to the 26 ions per second. And during storms, we have oxygen also, substantial amounts. This corresponds to maybe 50 to 100,000 tons a year of ions only. And then there's neutrons in addition, of course. But we also gain matter, actually. Accretion processes, various accretion processes include like dust, comets, and perhaps on a global time scale, large impacts, here illustrated by a crater, a comet, and some dust. So if you do calculations, trying to calculate these sources, the accretion is actually larger than the loss. The asteroid, meteorites, large impacts and so on, if you divide it, if you try to go second by second, it is actually a gain of 5 to 6 kilograms per second. The loss is lower, ions a couple of kilos, neutrons perhaps a kilogram. So over time, the Earth is actually gaining mass. So we should not be afraid of the sort of evaporating space, not in the near future. Interesting is, though, that what we gain is essentially minerals, metals, metallic constituents, and what we lose is essentially protons and oxygen, and actually water. So for other planets, of course, there's this question of habitability and long-term evolution and so on. So ion outflow or outflow at all, it's not really limited to the Earth. So I put up, we have observations from a couple of other planets in our solar system. Of course, the closer to the sun you are, the more illumination, the more irradiance you see. So, for example, Venus, closer to the Earth, is smaller than the Earth. So it also have a lower gravity. Outflow rate 10 to the 25th, but most of it is actually lost. Earth, significant loss, but most of it actually goes back to the magnetosphere. Mars, much smaller again, so lower gravitational potential, lower radiance, outflow rates of the order of 10 to the 24th, so 10th of the Earth perhaps. Most of the plasma from Mars is lost. So to summarize, very important, cold ions can now be measured. And we call that the upcoming MMS mission has the same capabilities as plasma. You have these two complementary instruments. So there's a great potential to do these kind of studies also with the MMS mission. Cold ions, they constitute a significant supply of plasma to the plasma sheet. And cold plasma is actually dominant in large regions of space, in particular polar cap, low regions. Outflow rates we saw of the order of 10 to the 26th, 50 to 100,000 tons a year. On average, 80 to 90% is recirculated, and there's more recirculation during disturbed condition. Only about 10% of what is actually escaping is directly lost into the solar wind. Of course, there are loss mechanisms in the magnetosphere with plumes, with plasmoids and so on. Fate, that is where they land, where they end up, is mainly governed by the collection. With that, I say many thanks.